Hello guys, welcome to another video of Take You Forward, Take You Backwards, the so-called tub. And today, the playlist of DSA presents you with another topic of time and space complexity. In this video, you'll be getting the all knowledge that you require for knowing what is time and space complexity and how will you will be using those things to solve a DSA problem. Let me quickly jump into the topic. So first of all, what is time and space complexity? Uh, So, time complexity and space complexity is nothing but okay. Let's take the example of time complexity. It is the time taken for a problem to get executed without any errors. So, the same goes for the space complexity also. The explanation. Okay. Anyway, I'll just tell you guys. It is the space taken by a program to get executed without any errors. When you guys hear the word execution, what do you infer from that? So, to explain that, let me jump into this part of the page. So yeah, this is you. This is you, and you're here. You're here, and this is you with your solutions to the problem that you see in the websites of LeetCode or any other website that you use. Mainly use LeetCode. Some people who follow Strivers, I think they will be using Code Ninja. Okay. This is you with your solution, and this is the backend of LeetCode. This backend of LeetCode has its own backend running for solving the solutions with the correct algorithm that it has for the problem that has been given to you. So this, if you submit the code here, your code goes to the algorithm that is already present in the backend, and after the code goes to that algorithm, and the answer that the code gives is taken as a test cases, and it is stored locally by the backend, and it gets compared to the expected result that is already stored. So if both the values matches, you'll be getting a green signal for telling that your solution is perfect. Or if that doesn't matches, then it might say a red signal that your code is error or something. But in order for this case to happen, your code should be in a boundary of good time limitation. If it is not, then it says that your code is it exceeds the time limit. Yeah. So what is time limitation and how it says that your code exceeds the time limit? So that is what we are going to see in this video. So time limitation. For example, I'll give you an example. You are there and your friend is also there who's trying to solve the same sum or the same problem that is being given to you. And you consider myself as interviewer. So I'm just judging you both with the solution that you give for the problem that I asked. So in order to judge your answers, like I have to judge which code is better and which code is optimal. So in order to do that, I will judge it by the time that it takes and the space that it takes. So that is the place where time complexity and space complexity is used. So for that, in order to measure the optimization of your code or to measure the time complexity, I need a measuring quantity that is called as big O of n. I'll write it here. Big O, sorry, that is not big O of n. That is big O notation. This I will explain in a while. So now you can write inside of big O notation like anything. Like you write big O of n, big O of 1, big O of n factorial, big O of n square, n log n, also log n, also wait, am I missing something? I don't think so. You can also write n cube, n power 4, etc. So yeah, you could write all these things. But what are all these things, and how does this tell whether your code is perfect or not, or it is optimal or not? So yeah, let me explain. So if your code, what is this? What is it? Okay, if your code has big O of 1, then your code is best. That it is optimal. It is optimal code, and this is faster comparing all other big O notation. And the next one, yeah, wait, I'll just write in the decreasing order of the rest of the big O notations. So the first one is big O of n. So this is greater than symbol, and this is big O of log n. Then the next one is big O of n notation. The next goes for big O of n log n, and I'll write it down here. The next one is big O of n square, and the next one it fills the space like big O of n cube, n power 4. n power 5, etc. I don't think there is 5 that exists. But anyway, and after this, there exists big O of n factorial. So this is the order. This is the decreasing order of bigger notation, and this is the best case, and this is the maximum case that you could use it for a code. So yeah. So what are these, and how these affects your code? Let me just explain you with some example that I've shown. Yeah. If you see it here. So this is a code where user gives an input, and he just with the given input, he just have to find the summation of how much ever the input he gives. He just needs the summation of those many inputs. So yeah, so this is the code that is being present here. So with this code, let me just show you. So for the first sentence that is being given here, which is sum is equal to 0, let us assume that it takes about 5 mu seconds to execute. And let us assume this print statement takes 5 mu seconds to execute. But what about this? This central piece of code, this is dependent on n number of loops because that is inside the loop of for loop. So yeah, this for loop tells that this for loop occurs for n times. So the sum is equal to sum plus I. This occurs for n times. So the time that it needs to get executed is n mu s. So if the user gives 1000 as input, this occurs for 1000 times. So it is directly proportional to n. So if you just give a total count of the time taken, that will be like 5 plus n plus 5. Let us assume that this n is like more greater than of 5. So then you don't have to consider this 5, this is 5. Then at last the persisting quantity is n alone. So your code's time complexity is dependent on this n. So because of that, this code's time complexity is big over yeah. So let me jump into this one. So this says that a user gives the input, and the summation. This sentence has 5 milliseconds to. Let us assume that it takes 5 milliseconds. Okay. Anyway, if you guys can ask the question that in this there is an n here. So if you can ask me that yeah, this particular sentence is dependent on n, you could just ask me this question. But I will say no, it is not dependent on n. It is dependent on n, sorry, but it won't take n seconds to execute. Why? Because whatever the n value that the user gives, it doesn't it doesn't mean that this particular statement has to run for n times. It's just one single statement. If you give any kind of n, it just occurs for one time, and with the formula that has been given here, that is n into n plus 1 by 2, just occurs for one, and then it just gives the solution. So whatever the input that has been given, it doesn't depend upon the time taken, that is 5 milliseconds. So how much ever, for example, if the user is 1000 or 10,000 or 1 million, this time is just 5 milliseconds always, anyways. So this will also take 5 milliseconds, and totally this will take 10 seconds. Whatever the input value that has been given to this, it will just take 10 seconds. So this value is not dependent for, so that this is constant. By this, let us say that the bigger notation will be of 1, that is constant. So this is the best case, as I told earlier. So this is how you uh, find the time complexity of a given sum or problem. Okay. For example, let us take a formula for int I semicolon semicolon and I less than n, okay, and I plus plus. So if you already noted down that the last time I told that this for loop occurs for n times. So the value is given for n, so that the for loop occurs for n times. What if there is another loop inside this for loop? One more for loop which occurs for n time. In j is less than n. Sorry guys, I'm bad at my handwriting. Just please adjust towards it. I promise I'll develop my handwriting further. For now, you just have to develop it. Sorry. Yeah, I hope you can understand this. This is j is less than n and j plus plus. So this is another n times occurring loop, and this is another n time occurring loop. So for this, what you guess the bigger notation will be? And I say the bigger notation is O n square. This is not n square. This is bigger notation of n square. And why? Because for I is equal to 1, Let us take for I is equal to 1. This for I is equal to 1, this loop occurs for n times. For I is equal to 2, it occurs for another n times. So for I is equal to n times, it occurs for n into n times. So that the value comes out to be, what is this? The value comes out to be n square. So that's why our big O notation is big O of n square. So I guess you can understand. And I've also explained more on about log n and n log n. So for that, let us take another example. So for binary search, for those guys who don't know what binary search is, uh, I guess you have to wait for another some what 5 or 6 videos for me to explain what is binary search. But I know most of the guys who are seeing this video might have already known the meaning of binary search. So anyway, for binary search, the big notation is login. Uh, so I'm taking the example of login to be binary search. So let me explain why it is binary search being the legal notation of login. Now let me jump into the topic of what binary search is. So if we are given with an array, where is this pen? If you are given with an array, so can you see this? If you are given with this array, 2, 3, 4, 5, and 6. So they're asking to find this four number. So what will you do in this binary search method? This algorithm involves having a low, mid, and a high. Oh, this is high, sorry. So mid will be the summation of both low and high divided by 2. So that will have the mid value. And the value will be compared. If the given value is in the range of mid to high, then the low will be discarded. And the opposite happens. If the value is given in the given range of low to mid, then high will be discarded. So that keeps on occurring until the value reaches a single value. For example, in this discarded thing is high, so the remaining thing is low and mid. So in this, low will be set up and high will be set up, and the mid will be found by the formula that I've already referred back to. That is low plus high divided by 2, and the discardation will occur in that place also. So this keeps on occurring such that the discardation is occurs in a logarithm. I mean, exponential way. So there are the discarded values or increases exponentially in every iteration that we do here. So that is why, for example, for the discardation that happens, we'll have the value of 2 power k. So that will happen till it reaches the value of n, that is less than n. So if you take this and we find the value of k, that if you do that logarithmic calculation, this goes here, that will be having log base 2 n. So this is nothing but logarithm of n. So this is an example of we go of log. I guess you can understand this, but if you guys don't know what binary search is, don't worry. In the further videos, I'll be explaining all about it. So don't worry. So just keep in mind that this is log and log. Okay, for those who did not understand this, I hope you guys might not have understood it because I didn't explain it well. But anyway, I will explain further in this. For example, now I'm sure you guys will understand. Okay. For int I less than m, and I is equal to I into 2. So this is 2, right? You presume that this is 2, okay? Wait, I don't have to. I don't want you to presume this. I'll just make it 2 itself. Okay, this is Paka. And now, if you take this as a for loop, the value of I increases twice for every loop. Let I be 1 for the first loop, and it goes to 2 at the end of the loop. On the next loop, it will be like 2 goes to 2 into 2, that is 2 square. And for the next loop, 2 square will be taken as an input, and it goes to the value of 2 into 2 power 2. And this goes on increasing. This will be like 2 power 3 and 2 into 2 power 3, and it goes on till 2 power k. And this value, I mean the iterations will occur till the value is less than n, because we have already mentioned it here. These values will occur till the till it is lesser than n. So that this is the stopping range of the loop. So if we do the logarithmic calculation in here for finding the value of k, this will be around log base 2n. So this is where you get an example of big O notation of log. So in the same case, if you take the example, where is it? In the same case, if you take it as an example, if there is another loop inside the same loop, saying that these first parts are the same and the last part is I plus plus I plus plus. So you already know that for this loop, the bigger notation is n. So if you combine these two loops, because this loop will have log n and this loop will have n, if you combine these two and if you find the bigger notation, at large you'll be having the bigger notation as a result as big O of n log n. So yeah, I think mostly I covered uh, most of the bigger notations and its examples. Sorry if you couldn't understand. Uh, I guess you can't even take screenshot of this page. I'm very sorry. Just understand the concept. Further in the videos, our upcoming videos, I guess I just have to develop my handling skills for sure, or else I couldn't see some increase in my subscribers. So I have to develop the skill. Anyway, you will be understanding. I hope you understand. I hope you understand. Don't let me down, guys. Now, now let me explain this case. Now this is the main case. So, guys, for those who wanted to have some more knowledge of this, just listen to this part of the video. Now, you take the n value as an input, and that is having the input is lesser than 20. So, for a program to occur in a website or any other backend processing, that will take about 20 million operations. 10 to 20 million operations are required for are not required. That could take up to 20 million operations. So this is the maximum that a program can take. Maximum amount of operations that a program can handle. So this is the input value that you've given. For the given input value, if you compare the 20 to 20 million operations, you could take this 20 to 20 million operations. You could do more number of operations to match to the value of 20 millions. So it will be like if you take 2 power n, 2 power 20, still you won't be matching the value of 20 million. Still you will be having lesser number of operations in 20 million. So this value 20 inputs mean that you could do many number of operations in the given value of input. So that means you don't have to mind about the optimal solutions. You can just do it by brute approach, or root approach is nothing but if you see a particular problem in DSA, first by looking at that, you will be having some intention towards the problem to give a solution towards it. So that is called brute force. Without even thinking which part of DSA, which structures or which algorithm you should use, you will be having some basic concepts of idea that you use to solve this. That is called brute force. That is called brute force. So brute force might not need optimal approach. It can do maximum number of operations like n square or n power factorial. Many operations can be done for the given value of the input in brute force solution. So that's why this n value that has been lesser than 20 will have bigger notation of 2 power n and n factorial. And this bigger notation will be an example of brute force and backtracking. Backtracking we'll be studying later in the playlist of this DSA tab. And if the value is lesser than 3000, comparing the value of 20 to 3000, this takes lesser operations comparing to this 20. So in order to reach 20 million, this 3000 will have to have operation that is lesser than the 20 that lesser than the operation that is being done by 20. So this means that you should be more careful than this 20 in order to give a proper output towards the solution. So yeah, so that means that you could do the n square method for this. So what is this? Okay, yeah, n square. So this will be like uh, 3000 square. So yeah, n square means 3000 into square or lesser than that. So this will be value of around 10 million or lesser than that. So the operations that you do on this 3000 is lesser compared to this 20. So for that you'll be using n square as the bigger notation. So for that, the examples of dynamic programming, which is the most advanced topic in DSA. Uh, yeah, that also I promise that I'll do in later part of this series. And yeah, if the value is around 3000 to 10 power 6, then the operations that you do to bring the optimal approach or the value that you do should be, I mean, the number of operations that you should have to do to bring it towards 10 million is less. You have to be very careful upon the operations that you do on this value that has been given to you. That should be around okay, 5 or n log into n, those number of operations that you should do to bring to this values. So that has an examples of two pointers, greedy and sorting and etc. I've already told you n log n, it will be on some kind of sortings and greedy methods, and log n will belong to binary search, which we have already discussed in this video. So for n greater than 10 power 6, you should have the minimal approach or minimal number of operations that you should do to not to exceed the time limit. So that is why you should be very careful when you do this when the input is greater than 10 power 6. So that will be the best optimal method that you do towards your problem. And if you do this, your code is considered as the best. And for example of these bigger notation of log n and bigger notation of 1 will be binary solution on the map. So hope you guys understand. Mm, for example, for the practical meaning of what these uh, what these things matter, what these things mean, like what is this n power 20 and n power 1000 mean, I'll just tell you. So if you take this problem as an example, if you see here, they have given a constraint here. So this constraint tells that the value should be around the time constant should be the value should be around 10 power 5. So 10 power 5, if you compare to the value that I've given here, so 10 power 5 is it comes under the category, the third category. It comes here. It comes here. I guess you guys can see. So this will have the bigger notation of bigger notation of n and bigger notation of n log. So this is how you find the time constant that has been given for your sum, for your problem in DSA. If you, if you scroll down, you'll be having this constant. And if the value is given as 20 or 1000 something, then you should have to compare to this value that is already shown. And that means that your bigger notation is 2 power n or n factorial. So this is how you should do time complexity, and I hope you guys understand. And now let's jump into space complexity. Okay, space complexity. Yeah, for the previous problems that we have seen, we've used the time to judge the problem, time to judge the each sentences. For now, if you take this variable, for example, n and n2, let us assume that that takes about 4 bits, and this takes another 4 bits, and this summation variable takes another 4 bits. So let us say that there are many functions also in this. The function is being called here. So these are like auxiliary space. These functions, print statement, and all the functions calling are called auxiliary spaces. So this takes the space around 4. So if you calculate the total, 4 plus 4 plus 4 plus 4, it takes around the space of 16 bits. So even the value changes, whatever the input the user gives, the value will be around 16 bits only. It won't change. It will be constant. So what will happen if the value is constant? That will be having bigger notation of 1. So this is the best approach, which I've already told. And if you take another example, where is it? Yeah, it is here. No, it is here. if you take this as an example, so this is, it takes another 4 bits, 44 bytes or 4 bits, whatever. If this array takes another uh, 4 bytes, and this print statements and auxiliary spaces takes another 4 bytes. Let us assume that. But for the given array, the size of the array changes with the given number of n. So if the given number of n is 2, the size of array will be around 2. And if the size is sorry, if the given input by the user is 2, then the array of size will be equal to 4, that is 8. And if the user given input changes, then the size of the value changes accordingly. So this is dependent on n. So at last, if you calculate the total n plus 4 plus 4, this value increases with increase in the user input. So this is O of n. So this is how you calculate space complexity. Let us assume, or let us take another example. This is a recursive function. So where you will be having, uh, so this is recursive. Let me explain this first. So for this, you'll be having 4 bits, 4 bytes. For this, you'll be having auxiliary spaces of 4 bytes, and this calling function will have auxiliary space of 4 bytes. There's no calling function here, so this is the only thing that has the auxiliary space, and this is also 4 bits because the value is constant. No matter what, the size of the fact doesn't change. Uh, Even the integer I, it doesn't change. It will be on the size of 4 only. So whatever the user input is given or anything, the value of fat, int, and I and n, it won't change. So this is the case of 1. So we understand. And for this is a really different case. So I want you to understand this further. So this is a recursive call function. So in this, what happens? So a number is taken. A number is taken. So this is factorial method. Number is taken and it is multiplied into the function of the lesser number. For example, let us take 5 as an input. So let us take this as 5. Okay, this is 5. Okay. This is 5 into function of 4, which is 5 minus 1. So this calls another function, which is 4 into function of 3. Then this calls another function, which goes on. This goes till the value of n that is given in the sum in the problem. So this is an auxiliary space function. The calling of function is an auxiliary space, which I've already told earlier, already referred earlier. So in this, the constant value, the variable values are constant, such as 4 bits for the n value, that is 4, and for another, yeah, that's all. For n value, the constant space is 4. But for the auxiliary space, it keeps on increasing because we are calling the function for each step. That is recursive. The recursive calling of function is occurring in this problem. So because of that, auxiliary space in this will be having an exponential or an increase that is dependent on n value. So if you calculate the spaces in total, 4 plus n is because of the auxiliary space, because the function is being keep on falling until the value reaches to n. So if you calculate the space complexity, that will be around n. So we go n is the answer for this. So I hope you guys can understand, and wait for next videos. For the next videos, I'll be handling problems in DSA. So from now on, I guess for those people who are following my playlist, now you are okay with the basics of how to solve DSA sums. But yeah, I didn't teach you any C++ basics. But now for to the persons who have already known C++, now with the time complexity and space complexity knowledge, you'll be able to solve sums immediately after seeing, because time and space complexity plays a major role in solving problems in DSA. So yeah, thanks for spending time watching this video. Uh, Hope I see you in the next video on DSA. Tuck. Also, please subscribe the channel if you want.